All right, we have a lot of conceptual stuff to talk about today, but I want to make sure you get your point for the exercise. So I just made the warm-up of multiple choice question that looks dangerously like the exercise. So go ahead and discuss it amongst yourselves and come up with any questions you might have. You could also pull up the exercise and see, it's launched, right? You could pull up the exercise and see if you have further questions. We'll chat about it in 3 minutes. All right, let's chat about this. Let's see, maybe we pull up the Slido and we see we've got 62 votes so far. All right, so on Friday we talked about this magical thing called dynamic programming, which honestly, terrible name. What a terrible name. I feel like it has no meaning to it. So let's see, what are our options? Dynamic programming, and I don't see any more votes coming in, so let's see how we voted here. Woo-hoo. Aha, interesting. Okay, we have as a group have generally agreed on an algorithmic optimization technique that reduces redundant calculations by recognizing the final solution is a summation of smaller subproblems. So let's talk about the other options real quick, and then I will talk about why I do agree that this is the correct option. Okay, so the first one was a programming technique used to dynamically allocate the machine running your logic to allow for larger scale processing. That is not technically the definition of distributed systems, but I was trying to trick you by finding some way to make the word dynamic at all apply to this. No, honestly, I don't know where the term dynamic programming came from. So it is not this answer. Unfortunately, even though I was trying to be really tricky and make it sound like it was a real thing. This one, a way to make recursion faster. I'm surprised it's the least popular because somebody afterwards could really argue with me that technically correct. But here's the thing, is dynamic programming, I talked about it almost exclusively in the context of recursive programming, because that is almost always when we are applying dynamic programming, but it isn't always necessary. It's not by definition only for recursive algorithms. However, all the ways that we use it, the really effective ways, almost always a recursion, but it is not by definition only for recursive things. Does make recursion faster when you apply it, though, to the right type of recursion. Then let's look at this one. When you store previous calculations in a memo to use in later recursive calls. That one also, you could argue, technically correct. Again, it is not by definition only applied to recursion. And also, we learned about a few different approaches to dynamic programming. The one that I hope you take away the most is the memoization. And this is a correct description of memoization, where as you calculate something, before you go calculate a new thing, you check, have I already calculated that thing, i.e. does it already exist in my memo? If it doesn't, go calculate it and store it in my memo. That is one of the approaches for how we can reduce redundant calculations. But there is also, remember, we could do it, instead of just storing them, we can do what we call the bottoms up or the top down, so that we sort of calculate in the more effective direction. Or if you remember, we got to that in Fibonacci, it's technically called that sliding window, where we just had 3 variables. They were kind of filling up and emptying out as we went through. So memoization is one of the sub-strategies for dynamic programming, but there's actually more beyond that. So this is sort of like a yes, correct, but it's more than that sort of situation. And that leaves us with this top one being the most correct. It is definitely an algorithmic optimization technique. That's probably the most accurate statement. And it is very key to recognizing that the final solution is a summation of smaller subproblems. Those are probably the 2 most important parts of that sentence. Questions about that? Okay, cool. All right, that's all I'm going to say on dynamic programming. We're going to move on today to some other delightfully theory-heavy things. Yay! But before we do that, I know our brains are probably more in the era of the exams. So, of course, reminder, we have an exam on Friday. If you're surprised, pretend you're not at this point. But also, because of my fancy experiment here, of course, it took us forever to finally get to your final midterm scores. But look it came out with a really beautiful natural distribution, normal distribution. We ended up with a median and a mean of 72, also bonkers. I don't know how that happened. So right now, I consider this to be a pretty appropriately scored, appropriate difficulty exam. Hopefully you're able to look at how your grade was calculated. We did do it sort of question by question with your skips and all of that sort of stuff in there. The regrades are open right now till Thursday. Thank you. Till Thursday, because we can only leave them open for so long because we got to turn things around. We got a bunch of grading that's going to kick off on Friday when we start to grade your exam too. So that's the exam 1 results. Hopefully this makes you feel a little bit better about going into the final exam. Like y'all did well. These are good scores. Okay, I know it's like really uncomfortable to get those initial scores back and be in our average around 50, but this shows me that we're in a good direction, okay, team? So hopefully you feel a little bit better about going into the final exam. It will function exactly the same way as the midterm exam. Hopefully we feel even more comfortable with the format and the types of things we're going to ask you to put into those free response sections. I promise you we have tried extra hard to make it like painfully clear what we want you to write in those boxes, but we forever march onward. And then also because they are amazing and superstars and they literally just want to support you, literally not even at my request, the TAs went and wrote you a practice final. Huzzah! And it has been posted. Thank you, Yafka. Shout out. And then also the TAs have offered to hold a final exam prep session for you here in this lecture hall immediately following lecture on Wednesday. Does anyone have any course administrative questions? Yes? Oh, so the midterm grades, you'll have to go to Canvas to see them because we had to do a bunch of magic behind the scenes, and so the final number should be in your Canvas grade. And I will tell you, I'm going to make my final grades based on what's in Canvas. There is some behind the scenes automatic Canvas to Gradescope integration, so I just click a button and it like moves stuff over. But just so you know, please do look at your Canvas grades. That's how I make the grades. So if for some reason that migration didn't work properly and you get a grade in Canvas that does not properly reflect what you think it should be, please send the CSE 373 instructor's alias an email ASAP, because that's the number I'm going to use to calculate your GPA. So do make sure that the grades in Canvas are the ones that you expect them to be. Though I respect that in Gradescope, they might not, perfectly represent it due to late penalties and whatever, all that fun stuff. Any other course administrative questions? Cool. Okay, great. Then let's move on, shall we? So, today and Wednesday, we are going to be talking about a little bit more sort of theory style things. I know this is not everyone's cup of tea, but I promise, if I was going to subject you to any theory thing, I think this is the coolest, okay? I've tried, I promise. But in order to get there, there is one thing that we need to talk about. So we're going to talk about this thing called reductions all day today. Reductions is just a fancy way of saying, hey, look, if I reframe this question, it looks like this other question. And I'm going to talk to you about that for an hour. Huzzah. Okay. So let's start here. Remember this thing called topological sort? This is just the same slide you've seen. Topological sort is an algorithm that will take in a directed acyclic graph and spit out a valid ordering. Now, there could be a few different valid orderings depending, but the valid ordering that comes out of TopoSort guarantees that all predecessors, all prerequisites come earlier than the things that depend upon them. If it helps for you to remember, I do think of TopoSort as like the class prerequisites algorithm, or I like to think of it as the like how I build the files in my computer algorithm, because that's literally how that is run. So that's TopoSort. I expect this to be revealed. Then, once upon a time, many moons ago, I introduced you to this concept of strongly connected components, but let's revisit it. So within a graph, there are sort of subsections of a graph that I might apply a unique definition to. And one of those subsections is this idea of strongly connected components, which is when we have a directed graph, a subgraph of that where every pair of vertices is connected by some path in both directions. So what that means is, here I have a strongly connected component because I can leave D and I can go to B, I can go to E, or I can go to C, and I can go back to D because there's enough edges to make that happen. And vice versa for all of these. So all 4 of these can like leave themselves and go to any other by any direction. But A is kind of like its own separate entity on this graph. It is not part of this happy family of 4 here. So even though it's by itself, we support independence. A is considered its own strongly connected component. So you might kind of see this graph and see, hey, there are 2 strongly connected components within this overall graph. I know the strongly connected thing can be a little confusing. Does anyone have questions at this point? Yes?
Do we also consider BDC to be a strongly connected graph?
Do we also consider BDC to be a strongly connected graph? So it meets the definition, but if you're looking for the entity that is the strongly connected component, you want it to include the entire set of vertices that are all strongly connected. So we wouldn't say carve off a sub piece of the strongly connected component and be like, this one's still strongly connected. We think of it as the entity of all the vertices that can leave and return to one another. Okay. So TopoSort, remember, runs in graph linear time. The algorithm defines strongly connected components, I will tell you, also runs in graph linear time. And now you might be like, okay, Casey, why do I care about strongly connected components? Well, I'm going to show you an algorithm and specifically a problem that really relies on it. But it's kind of a way to sort of like abstract away some of the more details of the graph. It's a way for us to sort of summarize the graph. So here you can see underneath my blue circles, that's a graph with like a bunch of vertices, a bunch of edges. But if I go through and I isolate the strongly connected components, I see that there's 4 strongly connected components. If I sort of overlay this new graph, we'll call it H, over those strongly connected components, it's kind of like I went from that really detailed graph under there to a graph of just 4 vertices that still follow the same topo logic. Like there's still like A can only go to B, B can only go to that cluster that we're calling cluster 3, 3 can only go to cluster 4. So it's a way for us to sort of put this like filter over the graph and abstract away the details, but maintain some of the key information, which is just that like connectivity, where we sort of consider all of the items within a strongly connected component to be like one singular entity. Why? Why do we care about this? Okay. So like I said, it's sort of like giving us a graph summary. The thing that's really amazing about it, like I said, is that it only costs us graph linear time in order to determine this sort of summary entity. Yes, fine. this is just written out versions of what I just said. I'll let you read it. Okay, so now we have these two techniques. We have topo sort, and we have the ability to find strongly connected components. And hopefully you believe me, and I tell you they run in graph linear time, which for our purposes, graph linear time is pretty much as fast as you're going to get, right? Like if I'm going to process my data, moving over and touching every piece of data, like one time linearly, is pretty much as fast as I'm going to be able to process this graph. Now, bear with me, we're going to go on a journey to think about how we can transform more complex human-style problems into a graph-modeled problem, and then apply these two algorithm techniques in order to find a particular answer. And what's weird about this is the first time where we're going to start to use edges to represent sort of transitions of state and logic, like we're moving away from using graphs to just represent physical directions or direct like relationship connections. Now we're kind of talking about logical connections. Okay, here is my example problem for you. We're going to call it final review. So let's say that I am writing the final exam. And I have a long list of problems that I can decide whether or not to select into the set of problems that are going to be on the final. You know, maybe I'm like, oh, I could have a sorting problem. I could have a graphs, like, let's say MST problem or a shortest path problem. I could have some PNP problems. I could have some dynamic programming problems. I've got these sort of entities of these problem topics. And I have the decision whether or not they will be yes on the exam or no, they will not. But because I am so nice and democratic, I want all of you to have a say. And so I say that every student is allowed to tell me their wishes for the exam, but they have to tell me their wishes for the exam in a very specific way. And the specific way is, guess what, so that I can feed it into this magical computer science solver and it will spit out an answer. So this is a little weird for us as humans, but it's about how we translate the complexity of this human problem to something a computer can understand. So if I was a human, I would probably just be like, tell me what you want on the exam. Tell me what you don't want on the exam. And maybe you'd all have some opinions this way and that. But one way for me to do it sort of structurally is to say everybody gets 2 votes. Everybody gets 1 vote for something they do want on the exam, and everybody gets 1 vote for something they do not want on the exam. So maybe you're like, yeah, I am crushing it with Kruskal's. I do want an MST problem, but that shortest path really ruined me, and I don't want a Dijkstra's problem. You would express those as sort of 2 Booleans that you're going to give me. And what I'm going to do is I am going to attempt to make a final exam that will satisfy one of your 2 votes. So I can't satisfy both of the things, but if you give me 2 options, I'm going to try and make sure that everybody has at least one satisfied. So if you're like, yes, I want an MST problem, no, I don't want a shortest path, well then maybe I will spit out an exam that has no shortest path on it. And then at least one of your 2 would be satisfied. Any questions on that framing? I know it's a little kind of like, well, it feels very inhuman, but you can tell I'm trying to break this down in a way for computers. Oh yeah, also this is not actually how I am making the final. The final is already made. Okay, so now one way we could do this is permutations. I could just take your 2 inputs and I could raise them to the number of questions and I could just spit out an exam of every possible combination, and then I could just run your logic through it and say, hey, does everybody have at least one of their Booleans satisfied? That would work, but it would run in this 2 to the q, if q represents the number of questions, times s, meaning the number of students, time. And so far, you probably haven't experienced too much of this, but I can tell you that this runtime will take so long that you probably could not run this for a class of this size. You probably couldn't run this on my dev machine at Google. You probably couldn't run this on distributed systems. Like, this actually is a runtime that ends up being so slow, you're probably going to run out of programmatic memory before you're able to finish this. So the permutation solution, while it would be nice, in actuality, computers aren't powerful enough, really, to run that type of solution. So what if instead we transformed this into a graph problem and we tried to figure out if those two things we talked about at the beginning of lecture could help us solve this problem? Because toposort and finding strongly connected components run in graph linear time, that's a very different runtime than 2 to the q. So you can do this. The way that you would represent it is every single possible vote gets represented as a vertex, and then the edges, you draw an edge leaving from something that would make somebody unhappy directed to a way that would make somebody yes happy. So let's say this is someone's entry to me. They said, yes, I do want a big O problem, and no, I don't want a recurrence problem. That's their 2 Booleans they gave me. So this no big O, this is the opposite of their column right here, yes. So this would make them unhappy. If I only give them 1 vote and that was the case, I could not make them happy. But I gave them 2 votes. And so the opposite of, or like this, the no recurrences, that would make them happy. So I'm going to put an edge moving from what would make them unhappy to what would make them happy. The formal way to say this is I'm going to make an edge from what would not satisfy to what would satisfy their requirements. We'll do another one. Where's my, there it is. So let's say they instead told me, yes, I want a recurrence, and yes, I want a graph problem. Well, then I could do this thing where I would have the arrow from yes recurrence to yes big O. As long as it lands on what makes them happy, I am okay. But this is not going to solve the problem for us. So there we go. We're going to go through and we're going to fill up our graph where we're going to make a vertex for every possible vote, and we will add an edge for every singular person that transitions them from a state of unhappiness to happiness. So the way that we would move through our graph, as you can imagine where we're heading with a sort of toposort type of thing, a toposort would order them from unhappy, hopefully, ending in happiness. I'm going to show you in more detail. So, there we go. Okay, yep, this is just more stuff that you can read when I'm not here standing in front of it. So we need a thing. We need to go from false to true or for unhappy to happy. We want to, whenever possible, avoid going from happy to unhappy, because then that might disrupt our possible creation. And the goal here is to take all of your votes, represent them as a graph, and then be able to run our algorithms that will tell us if the outcome, there exists some possible final exam that would satisfy at least one of your things for everyone. And I don't know. We don't know if there is. Maybe you all vote in a particular way that makes this impossible to do, but I would either have to do all the combinations in order to figure that out, or I could do this. So, what we are going to end up with then is we're going to end up with sort of a bunch of interconnections within our graph, and we might end up with a strongly connected component. Now, let's think about what a strongly connected component means in the context of this example. So remember, a strongly connected component is one where I can leave one direction and sort of one vertex and bounce around to all the other vertices before I leave to another connected component. And so in this particular case, what that would mean is all of the vertices that are strongly connected, well then hopefully they all represent a singular state. Like the students are still all satisfied, everything within that connected component contingent, or students are none of whom are yet satisfied. So the strongly connected components end up sort of sharing the same state of whether it is satisfying the problem or not satisfying the problem. So the first thing we would do is we're going to run the strongly connected components on the graph, but here's the thing right away that we can do, is if I have a question pair and they are in the same strongly connected component, like for example, let's say yes to this question type B and no to this question type B, if those are both in the same strongly connected component, and I can get back and forth between the two of them, then that means that there is no way to create a final exam that will satisfy everybody, because those two things are like mutually exclusive in the sort of context of satisfaction. And if they're in the same strongly connected component, it means there's too many people that want opposing things, and that singular strongly connected component will be both sort of true and false states for a bunch of people. So the first thing we do is we run strongly connected components and we check, hey, within each strongly connected component, do we have those sort of opposing options? Like, do we have the both true and false of the same question within the strongly connected component? If the answer is yes, darn it, the way y'all voted, we cannot create a final exam that satisfies all of you. But if that is not the case, if we end up running strongly connected components and they don't immediately preclude us from the answer by having these two opposite sides of the coin, well then those strongly connected components do represent that sort of state change where that entire strongly connected component satisfies everybody. And now what we can do is, if we run topo sort on those items, we would get out an ordering that would tell us which of those strongly connected components we need to sort of select in order to finally get the final exam that would satisfy everyone. So here is one possible orientation of the graph after I have gone in and I've made the yes and no per each question type, and each arrow represents a single student entry. I run the strongly connected components, I label them, and then I go through and I determine what that sort of state means for those students. And then I ask myself, once I call the ordering, do I ever transition from a false to a true? Do I ever transition from an unsatisfactory state or from a satisfactory state back to an unsatisfactory state? Then I can't do it. But if after I've topo sorted, I only transition from unsatisfactory, eventually landing in a satisfactory state, then I do have a final that will satisfy everyone. So as long as the strongly connected components, according to the topo sort, all end going from false eventually to all trues, then I can say yes, and then I will use that to make the final exam. I know this is pretty abstract. It's just one example of how we could take human voting logic and apply it into this graph. I don't actually care if you really know how this finding strongly connected components and topo sort thing works. You can dig into this. But technically what we have just done is we have taken this can I satisfy everybody's vote making the final exam from the 2 to the q times s runtime to graph linear runtime, because I just ran graph linear find the strongly connected components and then graph linear run topo sort. So this is a speed of algorithm that you could run on your computers. All of you could run this on probably your laptops. I could run this on my crappy Surface Pro here. Interesting. Now, if you take a step back, you realize that this is actually just sort of a generic way to represent logic. And actually what I have just demonstrated to you is a very famous problem in computer science. It is called the 2-sat problem. That's why I kept saying satisfaction, satisfiability, and it is just this problem where given a set of Boolean variables, each of the form variable 1 equals true or false, variable 2 equals true or false, find a setting of variables so that all requirements eventually evaluate to true. Just, can you take in 2 Booleans per entry, and can you end up with a final organization that satisfies those requirements? And you can see this is just literally like the pseudocode way that you would organize that. So this is called the two-stat problem. You could imagine, you could apply this to a lot of different scenarios, maybe with voting. Here is another problem that isn't quite so applying to our life, but is another common computer science problem. It's this two-coloring problem. Given an undirected, unweighted graph, color each vertex either red or blue such that the endpoints of every edge are different colors, meaning every individual edge has either red and then the other blue on one end of the edges. You can imagine scenarios in which this might apply. I didn't go through and find a real-world application for you. What? World maps. There you go. Sure. Like when you're coloring maps, you know how you don't want colors to touch so that it like shows up? Or like those state maps where you don't want the states to be the same exact color? Classic. Thank you. So you can, and this is just what two coloring is. There's a situation. So two coloring is just another application of two-sat. You can transform two coloring into two-sat. Where am I getting? Technically, this idea where we would take an existing problem and transform it into the format of a different problem, that's just what we call a reduction. Like I said, it's literally just a fancy computer science word for saying, hey, take this problem and reformat it like this other problem. But the reason that we might want to do that is because what if we already have the solution to one of those problems? Like, for example, we've kind of already been doing this, right? Like, we found a bunch of different ways to sort of interpret shortest path so that we could run Dijkstra's. We found a bunch of different ways that we could interpret our problems into the MST problem, so we could just run Kruskal's and we could get our answer out. So you've probably been naturally doing this, and I think the word reductions actually ends up in the P4 language, and I realized I hadn't formally introduced it to you. But reductions is just a fancy way to say, take your problem and translate it into something that we know already has a problem solver attached to it. There we go. So, for example, let's say we have a weighted graph, but I only know how to perform shortest path with unweighted graphs. Like it's before I taught you Dijkstra's and I had just taught you that BFS unweighted graph. So what we would do is we'd say, okay, well, here's the problem I have at hand. I need to find the shortest distance. And here's the tools in my toolbox. I have a shortest path, but it's only for unweighted graphs. Well, is there a way that I can cleverly reformat my problem so that it looks like the problem that I have a solution for? And so here's an example, right? Like if I have weights, well, maybe what I'll do then is I'll just put a bunch of dummy nodes in there so that instead of this overall edge being of weight of 2, well, now it is 2 because I stuffed one dummy node in there. This overall edge is now a weight of 2 because I stuffed a dummy node in there. Then I can run my magical algorithm on it, and then I just have to transform the output back. Again, you probably were doing this somewhat naturally in your brain, but this ends up being one of the most important aspects of algorithmic design and algorithmic usage in computer science, because all of us are trying to find algorithms that solve our problem. And wouldn't it be convenient if instead of trying to find an algorithm that solves my problem, instead I just found a way to transform my problem into your problem, and you already solved it for me? That's all we're doing here. So that's what reductions is. Now we're going to reduce the two coloring problem to the two sat problem. So there you go. Let's see. You could modify BFS to come up with two coloring, whatever. That would be our sort of brute force. let's say if we can just translate 2 coloring into 2sat, great, there we go. So what we would do is we know we need to describe the requirements in these terms of like 2 possible Booleans. And so then we would sort of make this thing where we've got, like vertex 1 is red or vertex 2 is red and the opposite. And so this is just a retranslations of that sentence that we had that was like, hey, the vertex on one end of the edge has to be one color, and then the vertex on the other end of the edge has to be the different color. I've just reformatted it into the Boolean logic that we can plug into our 2sat problem. Any questions on that piece? It's just reorganizing the logic. That's all that's happening here. Okay, cool. So here you could see then what we could do is when we look at our specific graph, we could start with C. So we could say is, let's see, you can see either A is red or B is red because they are connected. And if that's the case, then the opposite can't be red. That's what this first line says. It's sort of representing this edge right here. The second edge, A is red or D is red. There we go. And then the opposite is true, representing this edge. Again, we're sort of writing it edge by edge, just like we did with 2sat solver. The final exam, every entry sort of represented a single edge. Every entry represented a single Boolean statement. I'm doing the same thing here. Then I translate it. There we go. We go through and we find, can there be a way to actually accomplish that? This 2sat algorithm, that's us finding the strongly connected components, checking that nothing that is opposing exists within the same strongly connected component, and then running toposort. And that gives me this magical collection. A is red, true, B is red, false, so on and so forth. And then we transform our output, and there we go. We have applied the same algorithmic technique from 2sat to the 2 coloring problem. You could imagine, because 2sat is pretty generic, it's just like, give me 2 Booleans, right? You could apply that in a lot of cases. And I can tell you right now, 2sat is solvable in graph linear time. So anything you could translate into 2 Booleans, there is a bunch of code on the internet that you could go download that says 2sat solver. You can solve problems for yourself. So if you can find a way to articulate your problem into these sort of graphs of opposing Booleans and edges between them, then you can plug it in to a 2sat solver and get an answer. In fact, there's some with UI even in there where you don't even have to run the code yourself. It's such a common problem. Yes? So 2sat is a series of Boolean, we'll call them Boolean statements. And with that entire Boolean statement, there is 2 sort of entities within the statement. And it's usually organized like this, where we've got a Boolean on the left, a combinator, and then a Boolean on the right. And so in the final exam, we had, exam question 1 equals true, or exam question 3 equals false. And that would say that you want exam 3 and you don't want exam 4 item on there. So each sort of entry from each vote from a student is a singular Boolean expression, but within that singular Boolean expression is the combination of 2 choices. This variable set to true or false, and this variable set to true or false. Yes?
Going back to the 2sat kind of island description in that one picture, how do you know which one's true and which one's false? I didn't really pick up on that.
How do you know which island is representing trueness? So you do need to go through and sort of see which ones satisfy based on which entity. I don't even know if I have a good image in here. But you would do it based on following through where each of these was originally placed. Each of these edges was originally placed to satisfy someone. But then as you go through, like I said, if, for example, somehow you've got an edge that goes from a state to another opposing state, like if you have an edge that somehow connects no B to yes B, or from yes C to no C, that's when you get to the like, whoop, we've hit the wrong sort of situation. So that's really what we're looking for here, but we're checking that every time we place one of these edges, the edges are always transitioning from something somebody doesn't want to something somebody does want. Yes?
Is this similar to evaluating the truth table for a statement?
It is based on the logic of truth tables, yes. And since each of these Boolean statements are kind of complicated logically, there's two variables and each variable could have two possible entities, and then you combine them with an or. Like, we're sort of flowing through it in truth table sort of execution according to the logic left to right rules, if that helps. Yes?
On one of the slides, it talks about like false and true for each of the bubbles.
Mm-hmm.
Like, would it be, all of the second row of the bubbles were all true? I'm just wondering how that's possible for the bottom right bubble, since you have.
So the ordering when we run topo sort is apparently this, like, the bubbles, it's going to go from this false bubble to this false bubble to this false bubble, then it eventually will transition to this true bubble. Or sorry, where do we go? There's 4, sorry. There's 4, 5, 6. And so since this in order will end up going from all falses to all trues, there does exist a way. But if it didn't, if like these up here were all trues, and then all of these were falses, or they were just all falses, that would mean there is no sort of valid making.
I don't understand what
True and false means that this set of vertices with edges does satisfy that series of votes. Meaning we haven't invalidated somebody's vote either by saying, oh, both of the things you want can't happen. So each of the bubbles sort of represent that everything that's happening within there still satisfies everything that everybody wants, the state of it. Like I said, it doesn't really matter if you get these pieces of it, but what I can tell you and where we're headed for, which is hopefully more exciting, is here's what I will pose to the group. I told you that we can do this sort of like translation and reduction. Hopefully you can kind of see how I could take a lot of different things and kind of jam it into this 2-sat context. Like we could be voting about what pizza toppings we want, or we could be, trying to color a bunch of different graphs, whatever, right? As long as you can take whatever you're trying to figure out and transform it into a series of Boolean variables, and we give everybody exactly 2 choices, I tell you there exists a linear time solution. What if I gave everybody 3 choices? Do we think that the same logic will apply if I gave everybody 3 choices instead of 2? Any thoughts? I will tell you it's a little tough, right? The thing that's convenient about the 2 choices is there's actually only 2 possible values for each Boolean, true or false. And so that actually really dramatically helps reduce the complexity of this. If I gave everybody a 3rd option, the permutations of that would originally be 3 to the q times s, which definitely couldn't run on your computer. And I will spoil Wednesday's lecture and tell you, no, you definitely can't run 2-sat solver on if we gave you 3 possible variables. And actually, as it turns out, there exists no way in what we would call polynomial time, or reasonably efficient so that our current state of computers could run it. There exists no solution other than running all the permutations for a 3-sat. Which, for the most part, means that is thus an unsolvable problem in computer science. If you can break it down to 2-sat, cool. But if it's 3, that is beyond our current level of computational power. Yeah?
Couldn't we give ourselves more options if we went with integers, like 1, 0, -1?
So if you changed it to integers, it's still about the transition of state from unsatisfied to satisfied. And I will tell you, actually, in the computer thinks of true as the number 1 and false as the number 0. The fact that we call them true and false, that's just, we made that up. So this is where we're headed on Wednesday, is a bunch of computer scientists all over the world in about the 70s were trying to solve a bunch of really, really hard problems. And then one of them was like, I wonder if I write it in this super weird and uncomfortable way that Casey just forced everybody to listen to for 40 minutes called 2SAT, and then he found a solution to it. And then a bunch of other researchers were like, well, instead of trying to solve the problem by myself, I wonder if I can just reformat my problem into 2SAT, and then boom, they had a solution. And so somebody then wondered, what happens if I have a 3SAT problem? And a bunch of other computer scientists were like, whoa, okay, well, if you're working on 3SAT, I'm just going to work on translating my problem into a 3SAT problem. And now there exists thousands, if not hundreds of thousands of problems that have been articulated into 3SAT. And now the mystery remains. Is there a way to find a solution to all of these problems in a method efficient enough that our current level of computational power can solve? And I will tell you right now, we do not know the answer to that question. So come back on Wednesday. I'm going to take all of this annoying stuff, and we're officially going to learn what the heck P and NP mean. And we're going to talk about the greatest unsolved